You probably all know that a credit card has a 16 digits long number as its ID. Within the 6 digits, the first 15 digits are randomly generated, but the very, very last digit, called check digit, is calculated in a special way. It is calculated by an algorithm called Luhn algorithm, designed by famous German mathematician Hans-Peter Luhn. We're going to explain how Luhn algorithm works and some mathematics behind it. As we just mentioned, the first 15 digits in a credit card number, they're all random generated. Therefore, the minimum distance is 1. But by adding the last checking digit, we want to achieve minimum distance of 2. With a minimum distance of 2, we aimed to detect all single error and as many as transposition error as possible. Let's use the example to explain how a credit card is validated. There are 3 steps. First, we simply go through 16 digits. We double every alternate number. Let's use this as example. You can see the first digit is doubled to 8, 5 to 10, 7 to 14, etc., etc. Finally, 9 to 18. That's our first step. And after this round, you can see because we double it, some places we have 2 digits. Then our second step is simply check if anything greater than or equals to 10, we have to take 9 away to make it less than 10. Then here's the final calculation. We simply take all these new 16 digits, add them up all together. In this case, the total sum is 65. Then we need to mod by 10, result is 5. Then we check that value. It's only a valid credit card if n is 0. So in this case, because it's not 0, then we conclude this is not a valid credit card. We can tell the final result is 5. What if it's not 5? If it's 0, that would be correct. So we got 5 more. 8 take away by 5 is 3. So we know it would be alright if the last digit is 3. Only 3 placed there can make a valid credit card number. Shall we go back to example again, this time from a different angle? We look at the process how to generate that check digit. Previously is validate, now is how to generate. So initially we don't know what check digit is. Let's put question mark there. Still same, 3 steps. The first 2 steps are exactly same. We do doubling the number, work out sum, and change take away by 9. The only difference is when we reach the third step, we add them all up and then do the mod 10. This time we take negative value, then that will be the final result. As you can see here, total sum is 57 and the mod by 10 is 7. Then minus 7 makes 3. Why is that? Because 10 take away 7 is 3. That value is consistent with previously we worked out anyway. Just in case you're still not sure why minus 7 is 3, I'm here quickly draw a clock. We're under modular 10, and here is 0 o'clock. 5, 1, 2, 3, 4, 6, 7, 8, 9, 10. What does plus 3 mean? On this clock system, you go from 0, 1, 2, 3. That's where you are, plus 3. Then what's minus 7 means? You work towards to a opposite direction. 1, 2, 3, 4, 5, 6, 7. 7 steps in the opposite direction, we reach the same value. Therefore, minus 7 mod 10 equals 3. Now we're in a good position to do a little bit compare and contrast between 2 code methods we introduced. On the left side is ISBN. On the right side is critical number, which we just introduced. What things in common between two codes? They both added one redundant digit, increased the minimum distance from 1 to 2, and then they're both trying to detect single error, which is both achieved, and then they aim to detect transposition error as well. Now, on SBN side, we use a weighted sum, and then we do a modulo 11. But with credit card, we don't use weighted sum, we use a doubling neighbors sum, which is another kind of a weighted sum method. Instead, we use 1, 2, 3, 4, 5, 6 different weight. Our weighting system with a credit card is like we use 1, 2, 1, 2, right? So every neighbors, they have different weight, which is very clever. Then ISBN will be able to detect all the transposition errors. But because we use mode 11, we need to add a special value to represent 10. Well, with credit card, we use mode 10, then we can't detect 100% transposition errors. There are very small proportion cases we can't cover. But advantage is we don't need to worry about 10 appeared in the checking digit. If you're interested, you can check this example. If you have a 0 and 9 next to each other, and if you make mistake, write it as 9 followed by 0. That would be a situation we can't handle using current Luhn algorithm. Because you double 9 and then subtract by 9 back to 9 again. But it's only very, very small percentage. It's 98% we can cover. That's the end of our error detection topic. Thank you very much for watching.